So these are what I call real-world IMF questions. Mostly they come from old questions that I've seen in the biochemistry and medicinal chemistry options. So the first one is about vitamins and about water versus fat solubility, and this concept that certain vitamins are actually pose somewhat of a danger of overdose when you take vitamin supplements because they are fat soluble, as opposed to vitamins that are water soluble, which are nearly impossible to overdose on because if you have extra of them, they'll just be dissolved in your urine and you'll pee them out. Now, if we look at the structures, you can see that vitamin A has an OH group, vitamin D has an OH group, and vitamin C has lots of OH groups as well as a couple of oxygen atoms. So in thinking about the concept of water solubility, we're going to definitely notice that vitamin C is highly water soluble. And it's highly water soluble because of all of those OH groups, what we'd call hydroxyl groups, as well as those oxygen atoms, are capable of forming a lot of hydrogen bonds with water molecules. So vitamin C can easily be surrounded by many water molecules and therefore dissolved in water. Whereas these other ones, even though they can form a small number of hydrogen bonds off of their OH groups, most of both vitamin A and vitamin D, most of their structures are just made of carbon and hydrogen, so what we call hydrocarbon. And hydrocarbon is extremely nonpolar. And so since they're very nonpolar, they actually are much more soluble into your fatty tissue. So if you take these vitamins, they will sort of dissolve into fatty tissue and be stored in fatty tissue in your body. And that means that it's harder for your body to get rid of them. And normally you don't have too much of them, so it's not an issue trying to get rid of them. But if you really overdid it on a vitamin supplement, because of their fat solubility, they could actually pose sort of a health risk to you. All right, the next one, solid versus liquid fat. If you actually draw these out, the first one is what's called a saturated fat. It's saturated because it has only single bonds and it is saturated for hydrogen. And if you drew it out, the carbons form sort of zigzag but relatively straight tail. And at the end, you'd get this carbon with the O and the OH. So this is what's known as the fatty acid head, the hydrophilic portion of the fatty acid, and you get this long fatty acid tail, which is very non-polar. And then if you take this other fat, which is called linoleic acid, and you do the same thing, I'm going to just do this quickly. If you actually drew it out, after about 8 carbons, it looks like, you get a double bond. And the thing about double bonds is that they have a different bond angle, and they send the rest of the tail. Let's see if no, it's 2 in a row. Sorry, I did that wrong. So then we go to 1, 2, and then it would do another one. Whoa, that was wrong. Let's take that away. Let's see, 1, 2, 3, 4, 5. Okay, I did that quickly. These are just H's. But these are those 2 double bonds. I've drawn those, and they kind of form these kinks in the fatty acid tail, which has the effect of curling the tail up on itself. And this is a rather minor IMF topic, but that idea of straightness versus branching has an effect on surface area. So saturated fats, by being straighter, end up having more surface area and therefore more London forces. And those additional London forces from their geometry, from their straightness, actually means that they have higher melting and boiling points. So saturated fats are solid at room temperatures. When you look at a piece of bacon or a steak or something, or even chicken, and you see that solid white fat, that is primarily saturated fat. And when you have oils, like vegetable oils, olive oils, things like that, those are primarily unsaturated fatty acids. And the unsaturated nature, these double bonds that they have, cause the tails to sort of curl up on themselves, which reduces their surface area and their London forces, and therefore lowers their melting point. and so they're liquid at room temperature. So this one is a concept based on London forces and how geometry can affect surface area. Finally, which painkiller is stronger? Morphine and heroin. Heroin is a morphine derivative that can be synthesized from morphine. Now, to get into your brain, these painkillers have to dissolve across what's called the blood-brain barrier. And that blood-brain barrier is lipid-based, which means it's fat-based or non-polar. So if you look at these two structures, the only thing that's different about them is that in morphine there are two OH groups, which we know are really polar and are capable of forming hydrogen bonds. And in heroin, there's these groups instead. These are called ester groups. And while they are polar, they are not as polar as OH. OH really should stand out to you, that H-Nuff bond, as one of the most polar bonds that you can have. So these are more polar, and these are less polar. And because it's less polar, it can better dissolve across the blood-brain barrier. And so if you were to take heroin versus morphine, you get higher concentrations of the drug in your brain because of this very subtle difference in their structure and in their polarity. So again, it comes back to that concept of IMFs and solubility.